Good day, everyone. Our lecture for today will focus on graph sketching, more specifically on graphing some rational functions. In the previous lecture, you are able to graph polynomial functions by combining concepts on relative extrema, concavity, and using the table of signs of the first and the second derivative. In graphing rational functions, we will still need these concepts, but with the addition of asymptotes, which naturally arise when one deals with rational functions. We will be focusing only with rational functions that have linear asymptotes. This leads us to the first part of our lecture, a review on the vertical and horizontal asymptotes. Let's get started. We begin this part of the lecture with recalling the limit definitions associated with vertical and horizontal asymptotes to the graph of a rational function. You may want to revisit previous lecture on infinite limits and limits at infinity before continuing with this video. Alright, we will first recall vertical asymptotes. The definition is as follows. The vertical line x equals a is a vertical asymptote of the graph of f of x if at least one of the following limits is true. That is, the limit of the function f of x as x approaches a either from the left or from the right is either positive infinity or negative infinity. As you can see here, the following limits corresponds to the images on the right. For instance, this limit of f of x as x approaches a from the left equal to positive infinity corresponds to this image. Okay? Simply put, vertical asymptotes arise when there is an infinite limit at a finite point. Nice! Let us look at examples on finding vertical asymptotes. Consider the rational function f of x equals x squared all over 9 minus x squared. Let's first factor the denominator of this function. 9 minus x squared can be factored as 3 plus x times 3 minus x. Okay? Now, because of that, our candidate vertical asymptotes are x equals negative 3 and x equals 3. Why? This is because they are the values that make the denominator 0. As we know that infinite limits usually happens when the denominator approaches 0. Now let us check one-sided limits. First, we take the limit of f of x as x approaches negative 3 from the left. As x approaches negative 3 from the left, we see that x squared approaches 9, 3 plus x approaches 0, 3 minus x approaches 6. But since x approaches negative 3 from the left, say negative 3.5, 3 plus x approaches 0 through negative values. Because of this, we have positive all over negative times positive. This gives us that the limit equals negative infinity. Okay? So we proceed with other limits in a similar manner. Now going to the limit as x approaches negative 3 from the right. So the numerator doesn't change. Also 6. Now, since negative 3 from the right, 3 plus x approaches 0 through positive values. Hence, the limit of our functions as x approaches negative 3 from the right is positive infinity. Okay? So we move on. So actually, from limit as x approaches 3 from the left, you can check that the limit is positive infinity, while as x approaches 3 from the right, the limit is negative infinity. Hence, we can conclude that the graph of f has a vertical asymptote at x equals negative 3 and at x equals 3. Actually, you can conclude that it has a vertical asymptotes even if you only have one-sided limits going to infinity. Okay? But it is also customary to take the limit of both, to take both one-sided limits. Nice. Let's go on with the next example. We want to know the vertical asymptotes of the function x cubed plus 4x squared minus 5 all over x squared minus 1. First, we simplify. Actually, the numerator can be factored as x squared plus 5x plus 5 times x minus 1, while the denominator is a difference of two squares, x minus 1 times x plus 1. Hence, this f of x can be simplified as x squared plus 5x plus 5 all over x plus 1 whenever x is not equal to 1. Okay, you might suspect that the vertical asymptotes are x equals 1 and x equals negative 1 since they make the denominator 0. But let us compute limits to verify this. Now, if you take the limit as x approaches 1, so we can actually cancel x minus 1 since x approaches 1. You'll just get x squared plus 5x plus 5 all over x plus 1. You can substitute 1 there and you get 11 over 2. So we do not have an infinite limit, and therefore there is no vertical asymptote at x equals 1. Indeed, there is a removable discontinuity at x equals 1, which gives us a whole at x equals 1. So it is the whole 1, 11 over 2. Next, we take the limit as x approaches negative 1. As x approaches negative 1, the numerator will always approach 1, while the denominator will approach 0. Now, if we approach negative 1 through positive values, you can check that it approaches 0 to positive values. When we approach negative 1 from the left, it approaches 0 through negative values. In any case, the limit will become infinite. Okay? Which translates that f has a vertical asymptote at x equals negative 1. Nice! Now let's revisit horizontal asymptotes. Let's recall the definition. The horizontal line y equals b is a horizontal asymptote of the graph of f if at least one of the following is true. So you actually just get limits at infinity. So limit of f of x as x approaches infinity, or limit of f of x as x approaches negative infinity should be equal to that b there. Okay? So this is illustrated in the following image. These two, this and this one, illustrates the limit of f of x as x approaches infinity equal to b. Well, there are rests, this one below, limit of f of x as x approaches negative infinity equal to b. Hence, we have horizontal asymptotes when we have a finite limit at infinity. Nice. Let's move on with an example. Okay? So let's have a function x squared all over 9 minus x squared. Again, to get horizontal asymptotes, let's just take the limit as x approaches infinity. So either positive infinity or negative infinity. Let's first check as x approaches positive infinity. You know how to do this. You need to multiply and divide everything by 1 over x raised to the highest power of the denominator. So in this case, the highest power of the denominator is x squared. So multiply and divide by 1 over x squared, 1 over x squared. The numerator becomes 1, the denominator becomes 9 over x squared minus 1. And from there, we can take that the limit as x approaches infinity equals negative 1. Very nice. From here, we conclude that the line y equals negative 1 is a horizontal asymptote of the graph of f. Okay. You can also check that if you take the limit as x approaches negative infinity of f of x, you still get the same. You still get negative 1. Nice. Let's move on to the next example. Let's have f of x equals 2x plus 1 all over the absolute value of 5x minus 2. So we have an absolute value at the denominator. To solve this, we first make absolute value of 5x minus 2 into piecewise function. So it's either 5x minus 2 if x is greater than or equal to 2/5, or negative of that, which is negative 5x plus 2, if x is less than 2/5. Hence, if we take x approaches infinity, so since this is two positive values, x is positively large, and therefore we get the one where x is greater than or equal to 2/5, or that is 5x minus 2. Okay, so this becomes, limit of fx becomes limit of 2x plus 1 all over 5x minus 2 as x approaches infinity. We then again multiply both numerator and denominator by 1 over x. Okay, so 1 over x to get limit as x approaches infinity of 2 plus 1 over x all over 5 minus 2 over x, which of course equals to 2/5. On the other hand, as x approaches negative infinity, before that, we conclude that y equals 2/5 is a horizontal asymptote of the graph of f. Now, if we take the limit as x approaches negative infinity, so the main thing that will change is that since it is negative infinity, we're looking at negative values. So it's in this interval, x less than 2/5. So we get this part, negative 5x plus 2. So again, multiplying both numerator and denominator by 1 over x, you get this one, and you get negative 2/5 in the end. Okay, so just like this one, but now we have a negative 5. Okay, and hence we have another horizontal asymptote. The horizontal line y equals negative 2/5 is also a horizontal asymptote of the graph of f. So it is possible actually for a function to have two horizontal asymptotes. That's nice. Okay, that ends this part of the video. Okay, the next part of the video will focus on non-horizontal and non-vertical asymptotes, which we will call oblique asymptotes. See you on the next video.